Hi, welcome back to the Calculus 1 lecture series, and we're going to continue our lecture number 29, the substitution rule. And for the video number 1, we did several problems, and so for this video, we're just going to continue and finish some other practice problems here. Okay, let's go ahead, go to our lecture notes. Okay. So like we did all the way to here, right? So now let's take a look at this one. So here is the x cubed of the 2 plus x fourths. So remember, like when we did it before, we said the first things we need to see, do we match any existing formulas? We have a list of some very basic formula. If you kind of refresh the memories, right? So we have this one, the six trig function, and the exponential will be itself, those things, right? So those are the antiderivative, the fundamental antiderivative formula we got. So for this problems here, so for this problem here, so x cubed plus 2, the x plus 4. So the first things here, we need to see which fundamental functions I might be able to use. So like in here, I think maybe we can treat this 1 over as our function. Remember that? All right, so this could be our function. Then the next things here, we want to see which one could be our u. So we'll say, oh, maybe this one can be our use here. Then after that, the only thing left is this x3 and the dx, right? So those are the only thing left here. So now let's try to see if we separate like this, can we get the everything inside the integration sign to find its place, right? So we say the first, we say mu is equal to the 2 plus x4, all right? And then we'll say the du, you take the derivative of both sides. So what is the du's here is 4x3 dx. And then the 4x3 dx, this is pretty good. This is a match, this light purple, so we just highlight x cubed over x cubed dx. And we have this extra constants. For this constant, it doesn't matter. The constant, we can always just move over. So we divide by 4 both sides. So this is x cubed dx here. See here, so this is x cubed dx. So now let's take a look to see I can rewrite this integration. So this is the integration, and then my function, what is my function? We say is the ratio. This is my functions, right? Then on the bottom, 2 plus x4. So what is this? This is my u. Then the x3 dx is what? x3 ds is du over what? Is du over 4, right? Then I can move the 1 over 4, to the outside, and then here, this will be 1 over u du. Then this is the formula we are familiar with, 1 over u. What is that? It's the natural log u plus what? Plus c. And now don't forget, the last step, we need to substitute back, right? So this is 1/4 natural log of what? 2 plus x4, because this is all positive, so I don't need to put the absolute values here. All right, so this is what? This is C here. Okay, so now let's take a look at the next ones here. This is 7 to the negative x. So this looks very base, very similar, like when we talk about the antiderivative, we have a formula. We have one of the fundamental formula is like this, right? So if you still remember, we said if you have a to the x power dx, what is this one will be? So will be itself, right? Will be the ax. And then you need to what? Divide by the natural log a, right? This is our fundamental this is our fundamental formula. So like in here, so first let's identify which one I can treat as the function. So I know the exponents, right? So I'm going to treat this is like an exponential function. So I'm going to treat this one as a function. And now where is my, where is my u? And so, okay, because here, right, the fundamental, so I will treat this negative x is my u. Then the remaining, what is here? The remaining is this one's here. Okay, so now let's see, we'll be able to rewrite this into this 3. So I will say u is equal to what? Negative x, correct? Okay, so u is equal to negative x, and then the du is equal to what is negative dx. So, this is pretty good, right? So I have a dx over here and the match, and I only have a negative sign. Like I said, we don't have to worry about the negative. We can just times negative. So it's negative u is equal to dx. So that's good. I find a replacement for my dx. And now let's take a look. Let's rewrite this integration. So this will be what? This is my function. So it's a 7, right? So I'm working on the exponential function. So this is my function. Then the negative x is what? Is u, right? Okay. Then the dx is negative du. So I have a du. Then I put a negative sign here. Okay, now after that, now I can do it by using my basic formula. So this is what? This will be negative. So exponential function, when I take the integration, still will be what? It's the 7u. And then don't forget it's natural log a, so it's natural log 7 plus c, right? And now the final answer, this will be 7. Then you plug back what is u. Right, so your use here, you need to plug back is the negative x. So I would say this is 7 negative x natural log 7 plus c. Okay, now let's take a look at this one here. So this one, okay, so this one is like, okay, so this one is like a little bit complicated, but immediately you recognize, you say, oh, this is very similar like the basic formula we talk about. So if you kind of refresh your memory back to your antiderivative, then you say, this one is very similar like the one, like if I have 1 minus x squared dx, then what is our formula tell you? This is arc sine x plus c, right? So this is what we learned in the previous unit. And now my formula looks very similar, except this is 4. So I was thinking about, if I can change this one to the 1 minus x, then I might be able to find the integrations, right? Using my formulas here. So I said, okay, let's take a look. What can I do? So this is a 4 minus x squared. I want to change this to 1. So what I need to do, okay, so I said, let's try to do this. I factor the 4 out. If you factor the 4 out, this will be 1 minus x squared over what? Over 4, right? Then this 4, you can let it come out. The square roots will be 2. And then here, this will be 1 minus. So x squared over 4, I can simply write it as x over 2 to the square. Okay, so now, it's now, okay, so now let's see here. So this will be the 0, 1. And then this is this will be the 1 over 2, and the square roots of 1 minus x over 2 the square. And of course, this 1/2, if you want, you can move it to the front, right? So this is 0, 1. And then this is 1 minus, x minus over 2 to the square. So you take a look at this one. Oh, okay, so now you know what is your function. Your function will be this square roots and 1 over square roots, right? So this will be your functions here, 1 over square roots on the bottom. So this is a function. So now it's matching this basic formula. So what will be your u here? This will be your u, right? So the x minus 2 square will be your u. Let me be careful. I cannot, shouldn't, this is the squares, right? So it will be this one, just x over 2. And then in here, I have dx, right? So what do I have left? I have dx left, right? So now let's see, I can transfer that, okay? So it's a workable not. Okay, so I will say my u is equal to x over what? X over 2. And then the du is equal to 1/2 dx. Okay, that's good. I have a dx. I have this 1/2, so what I can do, I can times the 2 du equal to dx, right? Okay, so now let's take a look. I can rewrite this one. So this one will be, this is 1/2. Okay, so from 0 to 1. Okay, be careful here. So this is my function, 1 over the square roots. This is my functions, right? So this is the function I want to use, the fundamental formula here. So now here, this is 1 minus x over 2 is u. So what is here is 1 minus u squared. Then the dx is 2 du. So it's 2 du. Okay, now you say, oh, that's really pretty good. Then this 2 and this 2 cancel. So what I have here, I have 0. Okay, so here I need to be careful. It's not a 0, 1 because I need to change the bound, right? So here, now in here, this will be 1 over u squared du. So now let's take a look at this bound, right? So I know the u is equal to the x over 2. So the original bound is 0. So when x equal to 1, then what is u? U's bound become 1/2. When x equal to 0, what is u's bound here? Becomes 0, right? So now my new bound here is 0, 1/2. 0, 1/2. Correct? All right. So be careful about this new bound that we talk about, right? So this is 1, 0, 1/2, 0, 1/2. Because I have this transformation, I need to have this new bound. Okay, so after this one, and hey, this one is good. I can just apply, I can apply the, the arcsine formula. So what is the answers here? So this will be the sine arcsine u. And since I already transferred the bound, so I can just put this is 1/2 over what? Over 0. Then you can plug that in. So you will get the arcsine 1/2 minus arcsine 0. So what 1/2 is 30 degrees, right? So it's a pi over 6 minus 0. So the answer is a pi over 6 here. Okay, so this one is kind of like we need to be a little bit careful, right? Okay, so now for this ones here, the next ones here, I have a tangent 4 to 2x secant squared 2x. So for this ones here, I need to decide which one will be my function. Obviously, I think is this exponents are going to be my function. But then if I choose like this one, so for example, if I say, okay, I want to choose this one be my function. That means your u going to be secant 2x. Now, when you do the secant 2x, right? So if you choose this one, that means you're going to choose this be your u, right? So then the du, the second derivative will be secant tangent. So you got the actual secant and the tangent is here, but the tangent here is the fourth. So probably this is not a good way, because if you do this, you probably cannot replace everything inside the integration. So now I will say, okay, now let's try to do this one. This will be my function, the x to the fourth power, all right? Then after that, then you will choose the tangent 2x to be the u. Then what is remaining here? Remaining is the second square 2x. Now let's see if I do this substitution, can I rewrite this nicely or not, all right? So I will say u is equal to what? Is a tangent 2x, correct? All right, so then I will say take the derivative of both sides, so it's du. So what is the tangent's derivative? Will be the second square 2x. Don't forget, what is here? I need to do what? The chain rules, right? So I need to times 2 and the dx here. Okay, so now you take a look here. You say, oh, this is pretty good. Second square 2x dx equal to du. I have this extra constants 2. Doesn't matter. Constants will not bother us. So you put a du over 2. Then this is a second square 2x dx, right? So second square 2x dx is here. Okay, so now we can substitute. Let's try to substitute back here to see we get a good answer, good function or not. So this is tangent 2x is what is u. Then what we say this 4 is my functions, right? So it's so here is the function. Right? I want to use exponents. I want to use the power rules, so it's a function. And then we also see this light pink, this light purple one, the sign second square 2x dx equal to 2 du. So I will put this is 2 du, right? So I can move the half out. Then this is u squared du. And now the next things here is I need to do what? I need to find the, the bound for u, right? So I know the u is equal to the tangent 2x. Let's see, when the x original is pi over 6, so the pi over 6, so tangent 2 times pi over 6 is what? It's a pi over 3. So 60 degree, the tangents, what is u going to be? You're going to be square root of the 3, right? Then when the x is equal to pi over 8, when x equal to pi over 8, what is the tangent pi over 8? 2x is pi over 4. So pi over 4 is 45. So tangent 45 is equal to what? It's 1. Wow, okay, so my new bound, I change it to 1 over square root of the 3, 1 over square root of the 3. So here, right, so I have my new bound, right? Here's my new bound, I calculated from here. Now, we can do the, start to do the integration. So this is a fourth, right? Okay, so the integration will be mu to the what? The fifth over what? Mu over the fifth over what? Over 5, right? And then this one have a 2, so it's 5 times 2, this is 10. Then you have the square root of the 3 and the 1. Okay, so now if you plug in, then you will get this answer is 10 and the 9, the square root of the 3 minus 1. Okay, so that is how do you use the substitutions, right? So even for the definite integrals, don't forget, this is very important, right? Don't forget what you need to do here. You need to change the boundary to use, right? So this is very important. And sometimes the students forgot to do that, and then you're going to lose points in the exam or the homework. All right, so the last two problems really is not the, it's not the substitution. I put over here is just want to talk about, we call about the net area theories, right? So in here, I just want to mention the odd and the even function. So from this one's here, right? So we said sine x is what? It's an odd functions, right? So we learned this a long time ago. So it's an odd function. So if you graph the sine x here, okay, so the sine x is go something like this, right? and go something like this, continuous, right? All right, so here this is pi over 2, this is a pi, this is a negative pi over 2. And because the sign is an odd function, that means it's reflecting over the origin. So if it's an odd function, if your integration is here, if your integration bound here is symmetric to the origin. So like for this ones here, that means this is a pi over 2 to the negative pi over 2 here. Because it's a symmetric, so because of net value theory, we have this area, we have this area. But this area is below, you know, so we can do a color coding. So this area, the yellow area is below, and the green area is above, right? And because of here, you don't really need to carry out the integration. And then you can say the answer for this one is what? Is 0 because of the odd functions, right? Okay, so now let's take a look. This is x4 plus x squared. So the x4 plus x squared, this is what? This is an even function. Okay, so the even function, so what do we mean the even function? Even function is the one, you know, symmetric to what? It's symmetric to what? To the y-axis here, right? So for examples here, then if you have some function that go like this, right? So this will be a even functions, right? So now if you have the integration, so the same things here, if your integration limit is symmetric, okay, so that means, for example, if this is your negative a, this is your a. If it's symmetric, so what is you are trying to do here? So you are trying to find these two areas, right? So this will be one area here, and this will be another area here. And because they are even, and they're all above the x-axis, so the integration you really, so if this is the sum of your f of x function, so you really can just do the 0 to a, the f of x dx, then what? You times 2. Right, because you just need to do one integration. You can just do one side from 0 to a, then you times 2. Okay, so like for this problem here, so it will just be like this. So you will say this is 2, and so from where 0 to 3, and x4 plus x squared dx. Then you might wonder, so you might wonder, say, why I want to do that? I still need to do the integration. That's true. But if you do like this way, because now your lower bound here, right, is 0. What is good about 0? When you do the substitution back, you know, when you substitute the value back, the 0 is a lot easier than some big numbers later, right? Okay, so like for here, you will do this way. So this is 2. Right, so then the integration for this one is easy. So it's x to the 5th to the 5 plus this is x to the cube to the 3. So you can just plug in the 3 and the 0s here. So when you plug in the 0, it's a lot easier. And then you plug the negative 3 and try to be careful about the negative signs, right? All right, so now after you plug that one in, so your answer will be, this is the 5. So this is 3 to the 5th power plus 3, and this is 3 to the 3rd power minus 0, right? Because you can just plug in 0, it's 0. So your final answer will be 576. I hope I did this one correctly, over 5, see here. Okay, so the last two problems just tell you, you know, how to simplify your integration. If you spot that this is an odd function and then the integration region is symmetric, then it will just be 0. You don't even need to do the integration. Then if you spot that this is an even function and the integration limits is symmetric, then you can simplify it. It will just be you times 2 times you integrate one area, because now you can start from 0. It will make the integration a lot easier. You know, the finite, when you try to find the value, you know, you substitute the 0. Typical is easier than you substitute any other values, right? All right, that's it. Okay, so we have finished this unit, and this unit is just basically started the introduction about the different integration skill, and the first technique we learn is a substitution, and also we can use even other functions try to help us to simplify our integration. And then for the next unit, we're going to, you know, in the next few units, we're going to learn many different integration skills here. All right, that's it. Nice talk to you. Have a good day. Okay, bye-bye.